Hello everyone and welcome to the solutions video for Codeagon February by Trilogy interview bit, whatever. So Codenation did their hiring contest. It was on 5th February, that is yesterday, and it was a pretty difficult round, if I say so. And I was able to solve problem 1, 4 and 5. I also know the solution to problem 3, so this is what we are going to be discussing. And I will go from the easiest one to the toughest one so that if someone was not able to solve any, they can have a comfortable view. Anyways, so the easiest problem was the fifth one, and unfortunately I did it very late. So let's see. So this was the problem. We have a matrix in this problem. Okay, this is not a good color. Yes. I'm trying a new whiteboard, by the way. It's black, I guess. So we have a matrix n by m dimensions. I think this whiteboard looks pretty good. So n by m, and initially everything is 1 inside of it. Now what we have to do is we have to make some of these negative. So maybe let's make this negative, this negative, this negative. And after that, what we want is the sum of every column to be equal to 0. So if I want to make it negative, I'm going to want to make 2 of these negative. Similarly here, I'm going to want to make 2 negative, 2 negative, 2 negative, 2 negative. And we want to tell how many ways are there to make such an arrangement where every column sum is 0. So let's first of all take out the obvious case, which is n is odd. So if n is odd, that is there was, let's say, another column just like this, then we won't be able to make it 0 ever, because if we want to make sum of 1 and negative 1 equals to 0, we want 1, if they are k ones, they have to be k negative ones. But because it is odd, we cannot get an equal distribution. So that's one thing. So for odd, we cannot actually do anything. However, for even, okay. So for even, how do we do this? Well, let's undo everything. And if there were just even number of rows, then notice we only have to select half of the rows. So we just have to select n by 2 rows and make them negative 1. And we have to do it for m columns. And because everything is independent, it just, if this value is x, if this is the number of ways to make one column equals to 0, then we have to make m columns equals to 0. So the number of ways would be x to the power m, multiply x every time because they are independent. And that was the solution. In one liner, it was n by 2 to the power m. So this was the solution for even, and for odd it was 0. And I don't have my implementation with me because we had to code in their trash editor interview bit. Thanks for nothing. So that is why I don't have code, but that's what I'm going to do today. Just explain the approach behind the problems. So this was a pretty simple problem. Now let's look at the fourth problem, which was again pretty simple, I would say. Okay, before proceeding to fourth, I want to mention one more thing. So n here is less than equals to 1000 or something. Now if you want to calculate this n by 2, this would be obviously a very big number, and that is why we have to get everything modulo 1e9 plus 7. So you have to learn a little bit of modular arithmetic. So let me clear everything. How can I clear everything? Yes. So you want to learn a little bit of modular arithmetic, and it is like this, right? So n minus n by 2, no, uh okay, whatever. So n minus n by 2 plus 1. So this is this value, and then here it is n by 2 multiplied by n by 2 minus 1, and so on. Now, to calculate this value, you're going to have to learn what a modular inverse is, because when calculating the answer in mod, you cannot do it like n multiplied by n minus 1 and then divide by n by 2. You cannot do this because you're taking mod over here. So if you want to divide by something, you need to multiply by its modular inverse. So I'm going to call it mod inv. So you have to multiply by the modular inverse. So that is like this. And then it becomes, let me just erase this. So after that, it just becomes like this. N multiplied by n minus 1 multiplied by up to n by 2 plus 1. And then all the other terms get mod inverse. So mod inverse n by 2 multiplied by mod inverse n by 2 minus 1 up to 1. And if you want to know how to calculate mod inverse, because the mod, which is 1e9 plus 7, is a prime number, it is just equals to n by 2, or so mod inverse x is equals to x to the power mod minus 2. This is Fermat's little theorem. You can study it anywhere on Google, but I would recommend CP algorithms. But because this is not a tutorial for that, I will skip over it. Now let's look at problem 3 or 4. Yes, problem 4. Okay, clear. Let me use white this time. So here we have a knapsack, but it has infinite capacity. So we can put as many items as we can. And we are given n items. Each has some weight and some profit we get. I'm going to call it value because that's what it is often called. So we have weights and values for n items, and we want to put these items into this bag such that we get maximum value. But capacity is infinite, so we can basically put everything. However, there is a catch. If we put some value w, which is greater than a, which is a given constant, which is like some density or threshold, then every item which has weight, so every weight which is less than w minus a would be would drop out from the knapsack basically due to a hole. So we want to calculate with this constraint what is the best value we can get. So notice that if let's say this is the weights, okay, 1 2 3 4 5 6 7 8, and let's say a is 3, and you are putting this weight 7, then 7 minus 3, that is 4. All those values, so I think equal is also here. You can check in the problem, it's really irrelevant. So everything, yeah, equal is also here. So all the weights less than equals to 4 will come out of the knapsack from a hole, and so this range, I'm gonna use a different color, so this range would come out of the knapsack, and we will end up with this much. And if you want to calculate this value, okay, so if let's say we had written them in sorted order and we have some values, right? So vi, vj, vk, whatever, we can get this value using prefix sums, right? So prefix sum up to 7 minus prefix sum up to 4 is the sum of this subarray, and this is exactly what we have to do. So what we are going to do is, for any weight, so let me clear this. So for any weight, we have like weights 1 2 3 4 5 6 7 8. For this weight, if we are calculating, and let's say a was 3, Then we will calculate, if we are putting this weight, then what are the elements that drop out. So if we put this, these values drop out, and then we use prefix sums to get the sum of values in this range. That is one possible answer for us. And then we iterate to the next element and try the same thing. So we try, okay, A was 3. From 7, we remove this and take the subarray sum here of the values, not the weights. And that is another candidate for maximum answer. We do this for every possible I basically. So for here, here, up to here. And then we just take the maximum over that and we can get that. So implementation is like we sort the elements by their weight, and let's say their values is something like this, and then we will iterate from here up to right, and for every element we will check if we are putting elements up to this weight. So let's say 3, let's say 5, right? So I will remove everything which is less than 5 minus 3. So I'll take only this much, and this value I can get by prefix sums. Now again, I'm not going to explain prefix sums because prefix sums are prefix sums. You can study about it. It's very simple. If you don't know, don't worry about it. The motive of this video is obviously to explain the main ideas and give some implementational details for people. Okay, now this is slightly difficult problem, and in this problem we are given, let's try a new color. Okay, so we are given a tree, so something like this. And everything has a value assigned to it. So they're just index actually. So it is 1, it is 2, let's say this is 3, this is 4, this is 5, 6, 7, 8, 9, and 10. And they define the jealousness value of, let's say, this vertex 6. So the jealousness of this value is the number of elements, the number of vertices in its subtree. What is its subtree? This is its subtree, right? So the number of elements in its subtree that have a value or index of their label greater than its label. So this is 3, this is 4, this is 5. They are less than 6, but 9 and 10 is greater, so its jealousness is 2. Similarly, the jealousness of 5 would be 0. The jealousness of 2 would be 2, and for the 1 it would be just 9 because everything is bigger than it. And what we want to calculate is the jealousness of the jealousness of every vertex and sum it over. So the sum of jealousness of every vertex. So how do we do this? There are obviously multiple ways to approach this problem. I will tell one of the approaches I didn't use, and then I will tell the approach that I actually did use. So the more straightforward approach, now this assumes that if we have some sort of data structure that can do it for us, then we will be able to do it. So this is just a no-brainer approach. So what you do is you DFS, and for every vertex you try to see, using some data structure, if you can get all the vertices that are greater than this number, then you add that to our answer, and you can get all these vertices which are in its subtree using the Euler tool. I don't know what it is called. I think it's Euler. So you can get all the vertices in its subtree using Euler tool, and then what you have to do is see how many of them are bigger than it. So you can actually solve it offline, but I'm not going to go in detail in that approach. I'm going to explain now what I did, which is much simpler. Here you do not try, instead of looking like, okay, how many vertices are in the subtree of, let's say, this vertex, we do not see it like that. What we do is for every vertex we see what it contributes to the answer. So this vertex 5 would contribute how much? So if we take the DFS path, which is this is bigger than 1, so it would contribute 1 to the jealousness of, so jealousness plus 1 of 1, but not for 6. Similarly 10, if you were to look at the path of 10, that would increase, so path of 10 is this, right? So that would increase the jealousness of 1 and also of 6 and also of 5. So instead of looking for every vertex what would be its jealousness value, we see what is the contribution of every vertex. And how can we do this? Well, let's assume you're doing DFS traversal. Now you can just store what are the vertices that you have encountered. So this is making me really annoyed. Yes. Don't mind me doing pointless things. So if you're doing the DFS traversal, let's say we were at 10, then what are the things that are in the stack? In the stack there are 1, 6 and 5 vertex, and these are the only vertex that have 10 in its subtree, right? That's how DFS works. Now if I can know how many vertices in the stack are less than 10, then I can just add it to the answer. And there's a convenient data structure inbuilt in C++, at least the GCC implementation, and that is a policy-based data structure. You can read about it in a Codeforces blog. If you search PBDS Codeforces, that would be the first search result. So what it does is it stores a bunch of elements like any set, but it also allows order statistics query. So you can ask it how many elements are greater than some element in the set, and that is exactly what we want. So we do DFS and we store, instead of in a stack, in an ordered set, we store all the elements in the path. So I DFS from 1, right? I go to 2, I have stored 1 in my ordered set. Then I go to 8, I store 2 in my ordered set. And after doing the computation at 8, I go back to 2, and then I go to 7. And notice that when I entered at 8, I added it to my ordered set, but after I'm leaving it, I'm removing it from my ordered set. So this way we can make sure that only the things that come in the path from root to our current vertex, we only get those vertices. And so after going, so it would be like 1 2 8, then it back to 2, then to 7, then back to 2, then back to 1, and then we are at 6, and let's say we move to 5 and then 10. We will have these things in our ordered set, and if we run the order statistics query, we will get 3, and we add that to our answer and modulo it whatever mod we are given. So that was the approach for problem A, which is, what is the name? Okay, I don't know the name. All right, now third problem, or the fourth problem here, that I did not solve it, but I know the solution, so I'm gonna discuss it right here. So where is this problem? Yeah, so this is another tree problem. Okay, let's just use white. So again we have a tree, but this time it is much more difficult. So yeah, this is not a binary tree, that's why I drew the extra vertex. So we have a tree, and every vertex is given some value. So a1, a2, a3, a4, a5, a6, a7, a8, a9 and a10, and we are given a number d. Now what we want to tell is we want to count the number of pairs in this tree. So number of pairs of vertices. So let's say A1 and A10. And what we do is we take the simple path. This is the simple path, and we multiply the values that come in this path, and we take its mod over whatever the given value is. I think it's C. So let's say this is some value X, and if this value is equals to D, then we store this pair, or like increment our counter, and we just want to tell how many such pairs exist in this tree that have the simple path product with mod equals to the value D. This is what we want to calculate. And obviously n is 1e5, so we cannot run an n square simulation. That would be too easy. So let's see what we can actually do. Well, let's say we are at A2, okay, and assume, let's say we're assuming that all the pairs of vertices that have simple path going through A3, A10, A8, A9 and A4, but inside its subtree, basically in this zone, all these paths are already covered. Okay, so let's say all the paths here are covered. Now when we are at A2, we will say the number of paths in this entire subtree, that would be the number of paths that are in this subtree and in this subtree. So its subtree is basically this. So as you can see, I'm trying to do some DP over here. So that is, so if we store in DP I the number of pairs, so number of required pairs in subtree of I, then to calculate at some vertex, that is A2, so this is our state. Okay, now to calculate it at this some vertex, this would be obviously, so dp2 is dp3 plus dp10. So we see how many are in this individual subtree and in this individual subtree, and now we want to see how many vertices. Okay, so now we want to see how many vertices, vertex pair, sorry, so in this subtree, such that they go through A2. So maybe one is like this, maybe one is just simply this much, and one is maybe like this. Okay, so we want to calculate the number of vertex pairs that have A2 as an intermediate vertex, and so let's call that value X, and this would be our DP state. And if we keep doing this, we will be able to get the required value at DP root, right? So now only thing we have to think about is how to get this value X, and that's what we are going to try to do. So let's remove this. It's taking too much time. All right, remove. Okay, so how do we calculate everything that has the path going through A2? So let's see this situation, that let's say these two values X and Y, this path has the product D. Then let's see what we have here. So we want this quantity and this quantity, right? Let's say they are P and Q, so P times Q, that we want to be equals to D. But how do we get this? How do we get P? How do we get Q? And to get that, what we can do is with a pre-DFS, we can just store what is the product of path, the path product from root to some vertex. So from A1 we have stored for A3, for A7, for A6. So we have pre-computed it. And now what we do is, okay, let me remove it. So this value is Z, this value is P, this value is Q. So P is just our the product we have calculated, so product of X divided by Z, and Q is just product of Y. So product of Y means the product path product from 1 to Y divided by Z. So if you do this equation again, you get PQ is equals to D times Z square. So this is again a constant. You take its mod, obviously, right? So now we just have to count the number of integer pairs that have this, let's say, new value D dash, the product of D dash. So how do we do that? Well, here, if we were to store every number and its frequency that occurred in this subtree, and every number and its frequency that occurred in this subtree, then let's say D dash was 10, and here let's say 5 occurred 10 times, or 2 times, and here 2 occurred 1 times. So I will get 2 multiplied by 1. So basically, if this had 5 and this had 5, then going from A3 to these two things would give me the product of 10. So whatever its frequency is multiplied with the other frequency, that many pairs I will get. And I know this looked horrible, so let me redraw it. Okay, so it was like this. So here we draw it like this. This was like X, and now let's say this value was 2, and this value was 5, and this value was 5. Okay, and since D dash, which was D multiplied by Z square, and Z is this value, if this was 10, then we know that we can form 2 pairs, once by using this vertex and once by using this vertex along with this vertex, right? So that is how we have to do this counting. But this counting we have to do in a very special way, which is called small to large merging, because otherwise we will run into an n-square algorithm. So basically, let me explain. So if you were to do it naively, what you could do is get this. So let's say there is also a few more things, we don't care, right? So yeah, so if it was something like this, so first of all we get the frequency map for this subtree and frequency map for this subtree, right? Once we have this, what we can do is kind of like merge all of them and then iterate through each of them. First of all, remove them and then see that if we were to try every number here, how many other pairs I get in other subtrees. So that's the naive way to do it. But this would result in an n-square time complexity. Let me give you a simple example. Take this linear tree. Okay, so since you're at every step copying, you're copying the previous thing because you have to merge it. So initially you used 1, and then in the next step you will use 2, then in the next step you will use 3, then in the next step you will use 4. So that is why we cannot do it like that. What we have to do is we take the, so let's say there's one more, okay. So what we do is, let's say this has something else. We go through these frequency maps, and at one time we merge the smaller one into the larger one. And there is a proof that if we do this with particular values, so if we have n values and things combine to make form a map, so let's say they're like n dots, right? If things are combining to form a map, right? So let's say these two combine into a set, and now if I want to join this and this, putting this into this will require me less effort, obviously, because it is smaller. And if we do this, the time complexity to completely form the set would be n log n. And and one simple way to look at it is that how it grows. So it is initially 1, so any set is initially 1. Then since we are only merging less than equals to, we get a set of size 2, then we get a set of size 4, then we get a set of size 8, and so on. So that's why it is n log n. Not a rigorous proof, but fair enough, I guess. So what you do is, let me remove this. So you take the largest set of these, so largest frequency map, and then you one by one merge the smaller ones into it. And while you are merging it, so let's say this was the biggest, okay, I'm gonna call it capital F, and this small f1, small f2, you will merge the smaller f1 into the capital F, and while you are merging, you will check every key value pair in it. So let's say it has 2 3 times and 5 2 times, and let's say here 5 was 1 times and 2 was 20 times. So every time you're merging, and there are other things, you see, okay, what is d dash divided by 2? That is 5. Is that in that set? If it is, you multiply both of their frequency and add that to the answer. So 3 times 1, 3. So answer plus equals to 3. And then for 5 again, you try this and you get 40, 20 times 2. And you keep doing this recursively to build up towards the solution. And this is a classical small to large merging. I don't know why I wasn't able to do it, but this is how you have to do it. Now there is one another way to do it, and probably plenty more, and that is to use square root decomposition. Now even I also don't know how to properly do it, but the main idea is you root at the square root, not the square root, centroid. Yes, centroid decomposition. So you root at the centroid, and you see, okay, what are the number of vertex pairs that have path going through it. So let's say a vertex like this, and let's say another vertex like this, which have the product which is required, d. So after you calculate that, then what you do is you remove this vertex, and then because it was the centroid, all the remaining trees would be of size less than equals to n by 2, less than n by 2 actually, I think, yes. And so you can keep doing that, and it would be something like n log square n. I'm not entirely sure, but it's a direction of thought you can explore. So these are the problems that I knew and their respective solutions. There wasn't any code in this solution video, unlike my other videos, because I do not have code, and now I can write it, but the issue is it might be wrong. I don't want to give the wrong implementation, and let's see how a pure approach based video does. Like, if you people liked it, if looking at implementation is like a waste of time and you guys can implement yourself, because if you can, then that's a great thing. You should implement yourself. That is very important. And yeah, if you liked it, please leave a like, subscribe. I'm trying to get to 1 million subscribers, and the current pace is too slow. So hurry up and subscribe. And bye.